A 200 milliwatt, 405 nanometer laser beam hits a mirror at normal incidence. Assuming 100% reflection, A. Find the average force on the mirror by the beam. B. Find the intensity of the laser beam at the mirror if the beam covers an area of 10 to the negative fifth meters squared. Since it is normal incidence, that means the laser beam hits the mirror and then bounces straight back. This is like a collision problem, so we can use the impulse equation to find the force. So let's see, do you remember what impulse equation is? The impulse equals to the average force times time, which also equals to the changing momentum. Now it is an ongoing event, so we can just choose any amount of time to look at. In this case, it's probably the easiest to look at 1 second. And this will be delta P. And there are lots of photons hitting the mirror, so we can say there are n photons hitting the mirror in 1 second. And every photon has the same amount of changing momentum. So n times the delta P for each photon gives us the total changing momentum. This means we have to find the number of photons hitting the mirror in 1 second, and we want to find the changing momentum for each photon. The changing momentum for each photon is the final momentum minus the initial momentum. Let's say the final momentum is h over lambda. The initial momentum would be negative h over lambda because the initial and final, they are in opposite directions. So if I make one positive, I have to make the other one negative. So this gives me twice h over lambda. And this will be 2 times the h is 6.63 times 10 to the negative 34th. The wavelength is 405 nanometers. So this will give me a changing momentum for each photon equals to 1.64 times 10 to the negative 27th. And that's the standard unit, so it will be kilograms times meters per second. And we still need to find the number of photons hitting the mirror every second. We know that the power of the laser is 200 milliwatts and the wavelength of a photon. So we can find the photon energy for each photon first. And that's HF, that's 6.63 times 10 to the negative 34 times the frequency, which is c over lambda. C is speed of light in vacuum, 3 times 10 to the 8th, and then the wavelength is 405 nanometers. So this will give us a E for the photon energy, 4.9 times 10 to the negative 19th joules. Now in 1 second, the total energy would be 200 millijoules because 200 milliwatts means 200 millijoules per second. So in 1 second, the total energy from all the photons equals to 200 milli 10 to the negative third, this many joules. And that will equal to n photons times the photon energy for each photon. So this will give us the number of photons hitting the mirror every second, 4.07 times 10 to the 17th. Now I can plug these two in here. So average force, that is what we're looking for, equals to the n 4.07 times 10 to the 17 times the delta P for each photon, which is 1.64 times 10 to the negative 27th. And this will give us a force that's 6.67 times 10 to the negative 10th newtons. And that's our answer in part A. For part B, we're looking for the intensity of the laser beam. Intensity, by definition, it is the power per area. The power is the 200 milliwatts, and the 200 milli is 200 times 10 to the negative third. Area is 10 to the negative fifth. So this will give us 2 times 10 to the fourth watts per meter squared. What if I change one thing in this problem? Instead of hitting a 100% reflective mirror, the laser beam now hits a completely black surface. What will your answers be for parts A and B? If the photons hit a black wall, the photons will be absorbed. They will not rebound like this, which means the final momentum of the photons will be 0. That means it will be 0 minus h over lambda. Therefore, the amount of change in momentum for each photon will be half that much. Only h over lambda, not twice h over lambda, which means this will be halved. That means the force will be halved. As for intensity, the power will still be the same, 200 milliwatts, and the area is still the same, so part B, the intensity will not change. But the answer for part A, the force, will become halved.